Well, good afternoon. Thank you for dropping by. The whole concept behind this talk is to show that although building a model, designing a model, getting all the data, cleaning up all the data, doing all the training, that can be really difficult. Using the model does not have to be that hard. And in fact, it can also be a lot easier than it seems. A quick overview about myself. I've been building software for a long time. But more important than what I am or what I do for the purposes of this talk is what I am not. I mean that I am not a mathematician. I'm not a statistician. I'm not a data scientist, which means that even though I may disappoint someone, I cannot explain the inner workings of the models we are going to be looking at today. I can, however, explain them from an intuitive point of view, because it is always a good idea for people who are using a model to have an overview of how it works and how it does whatever it is that it does. Now, that also means that some of you may scream that I am an imposter, and well, that may or may not be true, depending on your point of view, although I would argue not. And the reason for that is that I, just like everybody else in this room, am curious. And that curiosity comes a long way back. Now, this picture is quite old. It was taken circa 1960. But it shows a very characteristic vehicle. That's a library on wheels. And these libraries were very common in Portugal until late 1990s, early 2000s. And in the late 80s, early 90s, when I was already old enough to care about books, I was a very frequent customer of these things. Every fortnight, one of these would drive into the village where I lived, and I would always be there returning books and getting books from it. And I would choose two topics. It would either be science fiction or a crime mystery. If you ask me why, well, at the time I would just say because I like it. But maybe it was the combination of the future of what it may look like from a technological point of view with the mystery solving and the riddle part of those crime novels. And well, it turns out that many years later, I became a software developer, which kind of combines things, the future with technology and the mystery of designing software, mostly riddled with weird clues that nowadays we call software requirements and witnesses that are, you know, your shareholders, your stakeholders, you need to barely interrogate them. And this is how my curiosity developed, and it continued to develop until about 2021, when I decided to sit down and say, okay, so mobile devices are becoming powerful, but just how hard is it to run a model there? Now, before I got there, I had to understand a couple of things, and I will just go through the basics in case people watching this remotely do not have them. A machine learning model is basically a neural network. And similarly to biological neurons, machine learning neurons, they have inputs and they have an output. Inputs have weights, which are determined during training, and basically they state which input is more important for that particular neuron to do its thing. They have something called a bias, which fundamentally is a threshold determining when the output becomes active. But the basic neuron has a fundamental weakness. The mathematical model is linear, and our world is unfortunately not linear. Therefore, you will see in many, many models the expression activation function. Now, this is a fancy term to say that a mathematical expression has been added, so to speak, to the neuron's output so that it becomes less linear and can therefore model the uncertainty of our world. Now, we all like to code, and we can just open an editor and start writing code to simulate the neurons and then calculate everything about them. But that's kind of a waste of time when very nice and very smart people have already written machine learning frameworks. Now, one of them is TensorFlow, the one I have chosen to use. It has a big community, and it also has the advantage of having a library called TensorFlow Lite. Now, TensorFlow, the whole framework, that's meant for running on powerful machines. But models can also be used in less powerful machines like phones or even microcontrollers or edge devices, because we do not always want to have to contact some cloud service to run the model. First of all, because we may not have an assured network connection to that service, or we don't want to deal with additional concerns regarding privacy. Because let's be clear, if we are running a machine learning model on the cloud and we are transmitting user data over there, then most likely there will be additional concerns regarding privacy that running the model on the device will take care of. Being TensorFlow Lite, it has a smaller footprint and is therefore able to run better on underpowered devices, but can also take advantage of hardware acceleration capabilities when present. We are still on the terminology step. Now, there is a definition that can be quite a mouthful that says that tensors are generalizations of matrices for higher order data. It's a mouthful. And the reason why I put this definition here for tensors is because the framework is called TensorFlow. The fundamental data structure in TensorFlow are tensors. Let's do a small visualization exercise. In linear algebra, tensors have what is called an order. In TensorFlow, that is called a rank. And this is extremely intuitive. Now, a zero-order tensor is nothing but a scalar, primitive type. Done. The first-order tensor has a rank with one dimension. That's an array of scalars. Simple. A second-order tensor has a rank with two dimensions. That's a matrix. It's an array of arrays. Clear. Then we have third-order tensors and fourth-order tensors. You already see where this is going. Now we got that out of the way, and building models is hard. And now, what I like to call the easy part, well, within reason, is when we decide that we have an idea, we are going to build an application, we have a model for it, and then we run it. Now, most modern phones come with prepackaged applications. Many of them use machine learning models. Now, one which is most certainly known to us all are the camera apps. They apply photographic effects. For this small demonstration, I picked a generative adversarial network. Because you will notice the generative name, it's going to generate new data. Now, in this case, the model is going to apply image transformations. These networks can have other uses. You can use them to restore data that is missing and it will appear out of nowhere, and also to run simulations. One thing I really find funny about generative adversarial networks is the training process. Because for the training process, you don't need one model, but you need two. One is called the discriminator, and the other one is a generator. Now, obviously, the generator is the one that we will use later in the app. But for training, you also need a discriminator. And the discriminator's job is to become really good at spotting fake data created by the generator. So the first stage of training is to get the discriminator good at understanding that the generator is generating fake data. The other step is to get the generator so good that it always deceives the discriminator. And then we repeat. There is competition between these two models. And if the world were ideal, we would repeat this cycle until we got to a balance. Unfortunately, that's not the case. People building the models are going to stop when the models are good enough. And the specific model for this application is called Anime GAN. And it just has one task, which is to transform a pretty normal, pretty standard picture into something that would appear just out of an anime movie. Now, I did not build the model. The model is open source, has been pre-built. All the code that you're going to see together with everything that accompanies it is in GitHub. The link is at the end of the presentation. But what I want to show you is just how easy it is. Remember that slide, the easy part? How easy it is to load a TensorFlow model and convert it into TensorFlow Lite. Now, in this case, we just need to instantiate the converter from a saved model, give it the model name. Now, this specific example needs an additional parameter because the model author has changed the name of the metadata. And then we have a model file. Then how do we use this in an Android application, for example? Using is, again, simple. We load the file into memory and we instantiate an interpreter with the model file and whatever options are available for that, for the interpreter, and make sense for our model. In this example, you can see that 3 lines above, we are setting options that we are telling the interpreter that it can use 4 threads because this model gains a bit with parallel processing. And to run the model, we simply call the run method on the interpreter to provide the input data, which in this case is going to be some image, and retrieve the output data, which in this case is going to be an image as well. Of course, that this is easy. It does not free our application from knowing which data and which format does the model require, or which data does it provide, but it is just like using any other library. And the interesting thing is that these things actually work. Let's just take a quick look at what will the model say about this audience. And I would say that has a pretty cartoonish side to it. Not too bad. It works on a modern phone. And there are other applications as well. Now, before we go to the next one, just one more bit of terminology, which you will see if you start looking at models, which is the definition of an embedding. In machine learning, whenever we talk about embeddings, we mean that we are representing points in some n-dimensional space, but with one very important property. Similar points are going to cluster together in that space. We will see why this is important afterwards. But in this case, one of the examples you have on slide is the relationship between a country and its capital. And we can see that, for example, if we look at the point representing Madrid, it is closer to Spain than it is to Japan in this coordinate space, which means that the association between those 2 points, between Madrid and Spain, is a lot stronger than within Madrid and Japan. If we were using a model trained on this data and we would ask what's the capital city of Spain, it would most likely answer Madrid. And the next application is something that again comes out of the box in many modern phones, which is face verification. I set out to think, okay, how difficult is it to build one of these things? Turns out, again, there are models out there, there are open source models that deal with face verification, and the way how it works is that we get a picture of a face, we have it go through the neural network, and the network is going to output an embeddings vector. And this embeddings vector identifies that face in that model's coordinate space. How does the verification part take place? Well, it's the usual stuff, right? We register, we save an embeddings vector of the face that we want to identify later on, and later we get a new embeddings vector with a new image. If those two are close together, then they represent the same image. If they are further apart, then they represent different faces. Now, the application itself works in Euclidean space, which is a fancy way of saying that it works in the same geometrical space we've all learned about in school. And it does a simple Euclidean distance comparison using a small threshold. And whenever that threshold is achieved, then, well, the faces are identical. Just out of curiosity, I would like to show to run the TensorFlow model on this machine, on a previously captured face, just to show you what does an embedding vector look like. And as expected, it is, well, an array of coordinates. Remember that conversation about tensors and tensor shapes at the beginning? Here we can see that for this specific model, the input of the model is a tensor with 4 dimensions. Now, because it deals with images, it follows a very well-known pattern. In this case, it expects one image of 112 per 112 pixels with 3 elements per pixel. That means it's a color image. And it is going to output one tensor with 1 element of 192 positions. Now, in this case, that means the model uses a coordinate space with 192 dimensions. A little bit difficult to visualize, but still interesting. Once again, to prove that this works, I have registered my identity previously. Now you can see that it is detecting faces among you, but it doesn't recognize them. Whereas if I point it towards myself, it will recognize me as expected. Now, of course, I have only one identity registered in the application, but if you want to play a bit with it, just come find me afterwards. That's not a problem. The next applications, they deal with natural language processing. And the fun part about this is that we have, again, new types of models which have memory. They are called the recurrent neural networks on the one hand, and the most evolved versions are the long short-term memory networks. They have memory because in addition to the input and the output of the neuron, that we saw initially, they have an hidden input and a hidden output, which allows to move data along each of the iterations, meaning that these models are meant to be executed iteratively throughout the same session, and therefore they keep context of what has been done previously. Now, this is important for processing languages because we all know that in many cases, words towards the end of a language, they refer to words in the beginning of a sentence. And if we don't have memory of the whole sentence, then we cannot work with language. The first example is a model that is meant to describe an image. This model, the show and tell model, again is open source, and it is made of two parts. A computer vision model will receive the image and transform it into an embeddings vector. And that embeddings vector will be the first input to the language model. That language model is then called iteratively and will generate a description in English for that image. Here comes the part of the application knowing what to do with the output of the model. This is a very common pattern with language models. They will output a big array with one entry for each word in its vocabulary, and each entry is going to have the probability of that word appearing next. In this case, what the application needs to do is to select the words with the best probabilities, use them to start forming sentences, and then at the end, eventually picking the sentence with the biggest probability of being the correct description. What I would like to show you about this conversion to TensorFlow Lite. The conversion itself is nothing out of the ordinary, but I selected two lines. Models can grow large in size. And one of the ways to reduce their size is to apply a process called quantization. Now, what quantization basically does is to reduce the precision of numbers, of the parameters used in the model. So if originally, for example, we have double precision parameters that occupy 32 or 64-bit each, then we can tell the converter to quantize them, and in this case, to reduce their precision to 16-bit floats. This will reduce significantly the size, the footprint of the model in terms of file size, in terms of memory usage as well. And also another detail, depending on the hardware where the model will be running, and remember this is TensorFlow Lite, it has support not only for mobile devices but for other kinds of devices as well. Depending on the hardware where it is running, it means that we can optimize the converted model to the most suitable floating point or integer format for that specific hardware, therefore achieving as much performance from there as possible. You may wonder though, okay, so if we reduce the precision, does that mean that the model's output will be less precise as well? Well, I would say probably yes. In most cases, though, it should not be statistically significant, although it is always important to evaluate the performance of the model after it is quantized. And that's the reason why, in this example, I have selected 16-bit floats for the computer vision model, but the language model is using the default values from the TensorFlow Lite converter, because I experimented and realized that if I would force the 16-bit floats, the file would be smaller, but the output from an empiric perspective would not be as useful as with the default quantization. Now, we can try again, and we can see how the model will react to a room full of people. Let's see what it says. This can be fun. It says that it's a group of people sitting around a table with laptops. Well, as far as I know, alcohol was not being served at lunch, so I can only guess that the model is hallucinating a bit, but it got the group of people right, which is already a nice start. That's not too bad, I say. I'm guessing that when the model was trained, no one has shown it an audience. Because when I experimented this on my previous kitchen apartment, it got it kind of right. I'm not sure what's the difference between a stove and an oven. There is no microwave in that picture. I don't know where it got it from, but it works. Kind of. It's fun enough. Now, generative models. The fun stuff begins because these models are all the rage nowadays. And I would just like to show you an animation that illustrates how most translation models work. And why the translation models? Because they use two blocks, one called the encoder, the other one called the decoder. And that's relevant for the next couple of slides. Basically, what they do is that the encoder has memory. So it is producing state. And then it sends the hidden state to the decoder. Through iterations, that decoder is going to, well, decode the state into the target, in this case, the target language. It could be something else. We could be talking about decoding it into images, whatever. And when reading about this, I wondered, okay, but now we have generative models, which are all the rage now, the GPT series. Can we run this in a mobile device? Well, GPT-2, we can. For one reason, most of modern phones, they have sufficient capacity to run GPT-2. The model itself is available within the TensorFlow framework, so no searching around for esoteric models. Although they do say that they recommend the phone to have at least 4 GB of RAM to run this thing. Now, if we consider that GPT is already way above version 4, well, let's see how that goes. But anyway, the thing is that a GPT is made of decoder blocks exclusively. It works iteratively, like the other language model we discussed. And it has something that is really nice from my perspective, which is a layer inside the decoder that is called a masked self-attention layer. It basically means that when it is processing a token, it will assign a probability to the tokens before it, and that probability is going to determine how strongly the current token is related to the previous ones. Now, in this example, it is saying that the current token, in this sentence, is associated most likely with the token robot. These associations will help the model to predict the next token in something that, well, makes more sense for us anyway. How does it work? Again, same thing. Token embeddings and an output of token probabilities. Again, one entry for each word. See, the principles are pretty much the same. The model changes. And on each iteration, the output token is picked based on the probability of it occurring given the previous, the previous input. This will end when the model outputs a stop token or when we just exhaust the maximum size for the output buffer. Now, generating text with the GPT-2 model is fun, but then I was wondering, could we, for example, use this text to create a summary? Because, well, one of the nice examples that people usually run when interacting with GPT-4 is to ask them to summarize some email or some text. It turns out that according to the paper, yes, we can. The authors have used the too long didn't read token that elicits summarizing behavior from GPT-2. And luckily enough, there is a workbook based strongly on a workshop that was given not by me, but by people who know a lot more about this than I do, at Google I/O 2023. And in the workshop, they load the model and fine-tune it with the Daily Mail and CNN dataset, which is actually useful for us. And what this version does is to combine the original article from the dataset with the too long didn't read token, and finally with the article highlights. The dataset contains the full news article and some highlights which are used as the summary. Then it goes through data selection, it goes through training. Just so you have an idea, this laptop can run the data selection. It takes about 26 hours. But it cannot run training, which if you want to try training the model on Google Colab, on the free version, it works just fine. If I remember correctly, it requires some 12 gigabytes of GPU RAM. And I would like to show you first the conversion method. Now, the conversion itself is not difficult. This is a new method. We can define helper functions with the conversion. But TensorFlow Lite, given its name, is a library that, well, it was meant for a low footprint, which means that there are some operands that are not supported by default and need to be explicitly enabled, and additional libraries need to be added to the application. And in this case, for this model, it even has custom operands. Now, this means that these operands were implemented in the model, in the TensorFlow format, but they do not exist at all in TensorFlow Lite. And that means that they need to be implemented as well to run the application in TensorFlow Lite. Now, thankfully, Google has provided an implementation which the application source code pulls in as a library. But this is just to say that it is possible to convert the vast majority of models to TensorFlow Lite. And we do not need to be an expert in creating those models, but using them, it becomes really, really simple. I say that at this point, probably the hardest job is to come up with an idea to use a model. Still, with GPT-2, even though it was a little bit harder to convert, using it remains exactly the same. We load the file to memory, we instantiate an interpreter with whatever options we want to provide to them. In this case, again, I enabled multi-threading. Running the model, once again, is very simple. In this case, what we do, we get the text we had too long didn't read, and we let the model do its thing. And in a modern device, it is actually not that slow, thankfully. You have seen one version of the summary, which the model has generated when I took this screenshot. But today, well, let's see what it says. Every time we run the model, as expected, we get a different result. And in this case, well, I'm not going to read the original text, but it was copied from a random article. I just went to the CNN website, picked one that was not too sensationalist, sorry, and copy-pasted the first paragraphs. And turns out that in this case, the model has generated a reasonable summary. I can tell this because I have read this previously, and this one actually makes sense. If we try again, it's bigger, but the model is trying. And as you can see, it is reasonably fast. A model such as GPT-2, even with the complexity it has, already runs quite well on modern devices. Now, I hope I have aroused your curiosity in the sense of, okay, then we can run some models in our applications. On the left-hand side, you have the URL and the code for the repository with a lot more code than what you have seen here, including the applications code, links to the models, everything that you can play around. One of the models is hard to convert to TensorFlow Lite, but there are the links there. And on the right-hand side, it's a link to the book that came out of this in 2021. So it's 2023. It's a little bit outdated, but the principles are still the same. And well, at least I hope that I managed to show you that although it can be very hard to build a model, using it can be very, very simple. Now, thank you for being here. We still have a couple of minutes. So if you have any questions.
Thank you very much. Yes, we do. Thank you very much. Yes, we do have a few minutes. Do we have questions?
So you showed TensorFlow can be used with C++. Is there any benefit, like it's faster?
C++, you meant?
Yes.
The code I have shown for the applications is Kotlin, your normal for Android applications. TensorFlow Lite itself is indeed written in C and C++. You can interface with the library from a C++ model. That's possible. Would it be faster? Well, the library itself is doing all the processing, which means that it doesn't really matter from which language or from which kind of artifact you are talking to. I'm not sure if that's what you were asking.
Yeah, I think so, partially. And you showed you could convert or let's say describe still images. Can you describe real-time images of moving objects, for example?
I would say that you could it's only a matter of finding the right model. Now, the model I have shown for this application, it was built to describe still images. However, that does not mean that you cannot find a way to describe a moving object, or having a better tailored model to process moving images and describing them.
I was just thinking in terms of, for example, I'm a blind person. I don't care that there's a plane in the sky. I would care about that there's a bicycle moving straight towards me. I don't know, does the modern smartphone have enough, processing power to handle live stream, understand where that object is going towards me, and can notify me?
That is a very interesting problem. That reminds me, one of the frameworks that is used in one of the applications, the face verification one, it uses the Google Machine Learning Kit. And the Google Machine Learning Kit also is again based on machine learning, and it uses object detection and motion detection, which you could leverage if you wanted to detect a moving object in a frame and calculate its direction, and eventually then apply some sort of description model to the object that you have extracted from the frame in order to tell you what it is. I would give it a try in that direction. So first finding the object and then extracting it and working with it. Is a phone performant enough to do all this? That is a good question. It is certainly performant enough to do object detection on a moving on real-time frames. Certainly. Now, describing the object, it depends on the model that you are using. This one for describing a whole image is probably a bit too slow, a bit too heavy, but I'm pretty sure that there are other models.